Okay guys, I'm back to continue discussing to you the theories of vibration. So we actually have finished the free and dump case. So now we move forward to the free dump vibration case. So in this free dump vibration case, you will notice that the damping term is now present, no? So this is the damping term. But the force is still zero. Okay, so your piece of T here is still zero, such that your equation now is a little bit more involved compared to the first one. And if we consider now dividing this equation by the whole equation by m, so we yield this simpler em, and finding the characteristic root to generate the solution to such differential equation is simply done by using a quadratic formula. Okay, so the quadratic formula serves as our guiding formula to address, no, this situation wherein we have here a quadratic equation. So in this particular equation, we can take note of the following. So of course, since it's a quadratic equation, there are two roots of p. In every quadratic equation, always there will be two roots. So the roots p1 and p2 may or may not be complex, or simply they may be complex or real values. And the third, the solution of the DAM depends on the nature of such roots, whether it's a complex root or a real root. And there are three possible cases for such a DAM. So this quadratic formula, which is written very popularly in terms of this equation, may be written in a simpler form, no? Which is equivalent to minus b over 2 plus or minus the square root of b over 2 squared minus c, provided your a equals 1. Okay, so this is the simpler formula for the quadratic equation, such that I use this one here, and this is a plus and a minus. So I have a p1 and a p2 here. Okay, my b over 2 is simply this one, the coefficient of this b. So this is your b, this is my c. Okay, and my a is 1. Okay, my a is 1. So this is simply omega squared c over m divided by 2 and c over m divided by 2. And this is your b over 2, negative c over m divided by 2. Okay, so I have now my two roots, and the possibilities are defined now in this. If c over 2m is greater than omega, what happens to this? If c over 2m is greater than omega, we will be having a what? A real root. Okay? So this is a real root. If c over 2m is equal to omega, then we have what? We will have this as 0, and still we have a real root. Okay? And if c over 2m is less than omega, here we will have a complex root. And we know that if we have a complex root, what did I told you a while ago? An imaginary or complex root will simply be giving you a trigonometric solution. And we want that because that's the easiest way to deal with the solution for differential equation. Of course, we can convert the trigonometric solution to an exponential solution, but it's more not difficult, but it is many references have provided us with trigonometric solutions rather than exponential solutions. Okay, so the non-vibrating case and here, which is overdamped, and the non-vibrating case here, which is critically damped, is not our concern. We're not interested with the non-vibrating case because what we want is for the system to vibrate, because this is a vibration subject, a dynamics subject. We want the system, the oscillator to vibrate. Okay? So if we substitute now the roots for case 3, so we now discard the two cases and only concentrate on case 3, then P1 and P2 may now be substituted in this solution, general solution in trigonometric. So the general solution is, if you will look into your references in differential equation, the general solution will simply be y sub t e, okay, to the a t multiply. Okay, a is now the root. If the root, this is the a of the root. Okay, a plus minus I square root, okay, of I think this is in terms of b. Okay, so that is sorry, we can make this simpler. Okay, so this is a. I'm just trying to relate it to what you can see on in your mathematical references. So is equal to bi. You call this the real part and the complex part. The complex coefficient has an imaginary part here, or real and imaginary. Sorry class, this is purely mathematics. I want to be very near to accuracy when I'm talking. So this is the imaginary part. So when you say complex root, it's a combination of a real part and an imaginary part. The real part goes to the AT there, and the imaginary part goes to the, so if I continue it here, this is now a cosine, okay, b t, okay, plus b sine b. So this is now the general equation that you may reference to when you are solving now the solution for such a vibrating case. Okay, so take note of this. Okay, so where did we get this? This is the b, no? This is the b, including the square root. This is the b, and this is the a. Okay. So let's define now more variables to simplify things, no? Medyo masyadong mahaba yung equation natin. So let's define a critical damping coefficient CCR to be equivalent to 2m omega or 2 omega m, okay, and define a damping ratio in terms of a C over CCR. So we can now define now a damp frequency in terms of an omega squared of 1 minus lambda squared. This is lambda, omega, which are Greek letters. Okay. Okay, so I'll show you the relationship of this later when we solve problems. So para hindi kayo malito ngayon, ganyan muna siya, no? So that we just want to simplify things out. Okay? This one here, which is the basis for our coefficient of t, becomes your damped frequency. Okay, and your negative c over 2m becomes your negative omega lambda. Okay? Okay, so how did that, paano nakuha yon? So, we simply substitute c is equal to lambda ccr. So, this is 2m omega. Okay, so if I divide this by 2m, so this becomes c over 2m is equal to omega lambda. So that's why there's a negative omega lambda there, because this is negative. Okay, okay, so this becomes a cosine omega dt. So itong b na to naging omega d, with kasama yung square root, and this becomes omega d. D is a subscript. It is not a variable, no? So it's a subscript. Okay, so applying the initial conditions now. So here, what's the initial condition? At time t equals 0, your your y0 equals yo, and your y prime of 0 is vo. Okay, so you will yield now this value here, no? So when you apply, I will just leave the mathematics for your exercise, plus please do it, no, because I will be giving you problem sets that will sharpen your a little bit your skills in differential equations. Okay, so I just like to compare the solution for this is a free dump, and this is the free undump. Okay, so yt is equal to yo cosine omega t plus, okay, so let's check it. Okay, yo cosine omega t plus vo over omega. Okay, plus vo over omega sine of omega t. Okay, so that's it. If you compare the two, they are just almost similar. Wala lang yung lambda, omega, yo there. Okay? Okay. So that ends the free and dump, the free dump vibration case. I will move to the force cases after this video. So thank you very much.